Every video on this channel takes more research than most people realize. If you want that effort to keep going, Patreon link is in the description.
The sun on your skin on an ordinary afternoon, that particular almost lazy warmth, is fusion. Hydrogen crushed into helium, 400 million tons of it every second. A violence so enormous and so constant that we stopped registering it as violence a long time ago. It became weather. It became Tuesday. We built our calendars around it. That star, the one responsible for every living thing that has ever existed on this planet, the one you have looked at since childhood through squinted eyes, is going to become a white dwarf. Not soon. Not in any time frame that touches anything we love. But eventually, in about 5 billion years, the sun will exhaust itself, shed its outer layers into space and leave behind its core, small, dense, silent. And that core is what we are here to talk about tonight. This is the Sleepy Physicist. And I want to say something before we begin. When someone joins the Patreon, they are not just hitting a button. They are casting a vote for the kind of content they want to exist on the internet. Careful, unhurried, deeply researched explorations of the universe are not common, and they do not sustain themselves without people actively choosing them. We are 24 co-creator members away from stable ground. And just to clarify, co-creators are the people supporting at the upper 2 tiers of the Sleepy Physicist's Patreon. 24 people making that choice is the difference between this channel wondering about its future and this channel knowing it has one. On Patreon there are over 50 episodes, audio biographies, comparison files, research notes and more. If you want to be part of that decision, the link is in the description. Now, back to what we are here for. A white dwarf is what remains when a star like the sun has nothing left to burn. No fusion, no outward pressure from heat. The nuclear engine has stopped completely. What keeps it from collapsing into something even smaller, a neutron star, a black hole, is not fire. It is not heat or pressure in any ordinary sense. It is a quantum rule. A rule so fundamental to how matter works at the smallest scales that the star's entire structure, its very continued existence, rests on it. We will get to that rule shortly. It is honestly one of the stranger things in physics. But first, the size. Because this is where most people's intuition quietly gives up. A white dwarf contains roughly the mass of the sun, sometimes a little less, sometimes more, compressed into a sphere approximately the size of Earth. Not metaphorically, not roughly. The sun's mass, the same mass that holds 8 planets in orbit, packed into something you could draw to scale beside our planet without it looking absurd. The density that produces is around 1 million times the density of water. A teaspoon of the stuff, if you could somehow hold a teaspoon of it, which you could not even close, would weigh somewhere between 5 and 15 tons depending on which white dwarf you are sampling from. The numbers shift a little depending on the source, but the order of magnitude stays grotesque. No light is being generated inside it, no new energy. A white dwarf shines only because it was once extremely hot, and it is slowly, over billions of years, releasing that stored heat into space. It is cooling, just cooling. The way a stone holds warmth after sunset, except the stone is as massive as the sun, and the sunset happened millions of years ago, and the warmth has barely begun to leave. That is what a white dwarf is. A remnant. A core without a star around it, held together by quantum law, growing slowly dimmer across timescales that make geological time feel hurried. And it looks from any practical distance like something finished. Something that has already done whatever it was going to do. It hasn't. For most of its life, a star is a negotiation. Gravity pulling inward, pressure pushing out, the two forces locked in an arrangement so stable it can hold for billions of years without either side gaining ground. The sun has been in that arrangement for about 4.5 billion years already. It will hold for roughly 5 billion more. On any human scale, on any scale that includes cities, species, continents, a main sequence star is simply permanent. Something the sky has always had and always will. But the negotiation does eventually end. Gravity does not forget what it is trying to do. The hydrogen at the core goes first. Not all at once. Fusion works from the center outward, processing the densest, hottest material first, leaving behind helium ash that cannot immediately burn. The core grows heavier with this ash while the shell around it, still rich in hydrogen, continues fusing. The energy from that shell pushes the outer layers of the star outward, slowly at first, then with increasing persistence until the star has swelled to dozens of times its original size. The surface cools as it spreads. The colour shifts from yellow-white toward orange, toward red. What was once a tidy, middle-aged star becomes something sprawling and diffuse, its outer layers barely held. This is the red giant phase, and it lasts a long time. Hundreds of millions of years, more or less. Though pinning it down feels slightly dishonest because the timescales blur at this scale. Inside, the helium core is contracting under its own weight, growing hotter. Eventually it reaches the temperature required to fuse helium into carbon and oxygen, roughly 100 million degrees, and it does so not gradually but in a flash. The helium flash. An explosive burst of fusion energy released in seconds, though almost none of it reaches the surface. The star absorbs it internally, restructures, settles into a new configuration. From the outside, nothing dramatic happens. A rearrangement, quiet and total. The star then enters what astronomers call the asymptotic giant branch, a second phase of swelling and instability where the outer layers pulse, contract, pulse again. The star begins shedding mass in earnest now, driven by stellar winds that thicken over time, peeling away layer after layer into the surrounding space. This material drifts outward in an expanding shell. When the ultraviolet radiation from the contracting core eventually reaches it, the shell lights up, glows. The colours depend on the chemistry. Oxygen tends toward blue-green, nitrogen toward red, and the structures that form are some of the most geometrically strange objects in the galaxy. These are planetary nebulae, which have nothing to do with planets. The name was given by early astronomers who thought they looked like planetary disks through small telescopes. They do, a little. What remains at the centre, after the outer layers have drifted away, is the core. Carbon and oxygen mostly, compressed by the star's own gravity and now exposed to space. It's extremely hot at first, temperatures exceeding 100,000 degrees, and it glows intensely despite being tiny, roughly the size of Earth. The planetary nebula around it catches that radiation and blazes for tens of thousands of years before thinning and dispersing into the interstellar medium. And then the nebula is gone, and the core remains. Just the core, cooling now, no longer surrounded by anything it once held. Something vast and luminous reduced to something small and alone, and very, very quiet. The silence that follows something large passing through is its own kind of presence. The star is gone, but what it left behind is still there and not quite finished. Imagine pressing your palm against a wall. The wall does not move. You push harder. Still nothing. The wall is not pushing back because it is hot or energized or angry about being pushed. It pushes back because it is there, because matter occupies space and refuses, at some level, to stop occupying it. That refusal is familiar. It is the basis of every solid surface you have ever touched. Now imagine the wall is made of something that refuses to compress, not because of physical bulk, but because of a rule written into the fabric of what electrons are allowed to do. That is a different kind of wall entirely. Inside a white dwarf there is no fusion, no heat being generated, no outward thermal pressure. What holds the star against its own gravity, what keeps a sun's worth of mass from collapsing further, is this. Electrons cannot share quantum states. Two electrons with the same energy, the same spin, the same position in space cannot coexist. The universe simply does not permit it. Pack matter tightly enough and the electrons run out of available states, fill every slot they are allowed to occupy, and then, when you try to compress further, they push back. Hard. Not because they are hot, not because anything is moving faster, because the only alternative is an arrangement the laws of physics forbid. This is the Pauli exclusion principle, named after Wolfgang Pauli, who worked it out in 1925, though worked it out makes it sound tidier than it was. He identified a pattern in an atomic behaviour that was real and consistent and deeply strange, and the strangeness has not really faded since. What Pauli found was that certain particles, electrons among them, are fundamentally antisocial at the quantum level. Each one demands its own state. Crowd them and they resist. Not metaphorically. Physically, measurably, with a force you can calculate and a force, it turns out, that can hold up a star. The pressure this generates is called electron degeneracy pressure. And the thing that makes it genuinely odd, and I think this part deserves a moment, is that it has nothing to do with temperature. Ordinary gas pressure depends on heat. Cool the gas and the pressure drops, but degenerate electron pressure does not care about temperature. You could cool a white dwarf to absolute zero and the electrons would still be pushing back. The pressure is baked into their quantum identity, into what they are, not how hot they happen to be. So a white dwarf is not warm in the way that matters for its structure. It is warm because it was once a stellar core, and it is still radiating that old heat away. But the warmth is not doing the structural work. The electrons are. And they are doing it silently, without fusion, without fire, through sheer quantum stubbornness baked into the nature of matter itself. Is that really what is holding it up? A rule about identity rather than force in any conventional sense? It seems like it should be less stable than fire, less reliable, but the evidence is clear. White dwarfs have been sitting in this configuration for billions of years. The wall holds until it does not, because this pressure, extraordinary as it is, has a limit. As a white dwarf gains mass, the electrons must be packed tighter and tighter. To maintain their exclusion from each other under increasing compression, they must move faster and faster until their velocities become relativistic, until they are moving at a significant fraction of the speed of light. At that point, something changes in the mathematics. The pressure they generate begins to increase more slowly than the gravitational force bearing down on them. The two curves, once balanced, begin to diverge. The wall does not shatter. It does not announce anything. It simply becomes insufficient. And what happens after that is not quiet at all. You have picked something up before and found it heavier than it looked. A paperweight maybe, or a piece of metal that seemed modest until it was in your hand. The weight was surprising because the size suggested something lighter. Size and mass, in ordinary experience, move together. Bigger things weigh more, smaller things weigh less. This is so consistently true in everyday life that it operates below conscious thought. It is just how that objects work. White dwarfs do not work this way. Add mass to a white dwarf and it does not grow. It shrinks. The more massive it becomes, the smaller it gets. This is not an approximation or a tendency. It is a direct consequence of the physics holding the star together. In a normal star, adding mass increases the internal temperature, which increases the pressure, which pushes the star outward to a new, larger equilibrium. The relationship between mass and size is cooperative. In a white dwarf, where electron degeneracy pressure does the structural work, the relationship runs the other way entirely. More mass means stronger gravity. Stronger gravity forces the electrons into tighter configurations. Tighter configurations generate higher degeneracy pressure, but they do so by making the star physically smaller. The star does not expand to compensate, it compresses further. This sounds like it should lead somewhere stable, and for a while it does. A white dwarf of roughly half a solar mass sits at about the radius of Earth. One with a full solar mass is noticeably smaller. One approaching 1.2 or 1.3 solar masses is smaller still, compressed to something closer to the size of a large planet. The relationship holds and the star holds, and everything seems not quite fine but functional. Each additional unit of mass met by additional compression, the star reorganizing itself inward rather than outward. What this means physically, though, deserves a moment. The electrons inside a more massive white dwarf are not just more numerous, they are more confined, forced into less space. And because quantum mechanics constrains how electrons can be arranged, they respond to confinement by occupying higher energy states, moving faster. In the most massive white dwarfs known, those above 1.2 solar masses, the electrons in the core are moving at velocities that begin to approach a meaningful fraction of the speed of light. Not all of them, not uniformly, but the trend is real, and it matters for what comes next. Here is the part that takes a moment to sit with. In normal matter, there is always more room. Compress a gas and it resists, but in principle you can keep compressing, keep adding mass, keep forcing it smaller, and the object accommodates. White dwarfs have a ceiling. The inverse relationship, more mass, smaller size, cannot continue indefinitely. At some point the electrons are moving so fast that the degeneracy pressure they generate stops scaling the way it needs to. The mathematics of relativistic electrons and gravitational collapse diverge. The shrinking does not bottom out at some small stable size, it simply does not stop. And the star that once seemed to follow a clean inverse rule, heavier means smaller, always, reliably, reaches a mass where the rule no longer saves it. What that mass is, and what it means, is where this goes next. In 1930, a 19-year-old named Subrahmanyan Chandrasekhar boarded a ship from India to England, carrying a calculation he'd worked out during the voyage. He was heading to Cambridge to study under Arthur Eddington, one of the most respected astrophysicists alive. The calculation concerned white dwarfs. Specifically, it concerned what happens to electron degeneracy pressure when electrons are forced to move at relativistic speeds, and it produced a result that Chandrasekhar found both clean and deeply unsettling. There was a maximum mass a white dwarf could have. Above that mass, the pressure would fail. The star would have no stable state to fall into. It would simply keep collapsing. Eddington rejected it publicly, called it a reductio ad absurdum, a conclusion so strange it must indicate an error somewhere in the reasoning. He said this in front of colleagues at a meeting of the Royal Astronomical Society in 1935, with Chandrasekhar in the room. The calculation was not wrong, Eddington was. It would take decades and a Nobel Prize in 1983 for the number Chandrasekhar derived on that ship crossing to be fully absorbed into the canon of physics. The number was approximately 1.4 times the mass of the Sun. To understand what that number means physically, you have to follow the electrons again. As a white dwarf accretes mass, gains it from somewhere, a companion star perhaps, or a merger, the additional gravity compresses the interior further. The electrons, already occupying every available quantum state, are forced into smaller volumes. To maintain their exclusion from each other in less space, they must move faster. In the most massive white dwarfs, the electrons in the core approach the speed of light. And here is where the physics changes, specifically and irrevocably. Relativistic electrons generate degeneracy pressure that increases more slowly with density than non-relativistic electrons do. The pressure curve, which once kept pace with gravitational demand, begins to fall behind. Add more mass and gravity gains ground. More mass still and gravity gains more. The star shrinks not to a new stable size, but towards something that has no stable size at all. What Chandrasekhar showed, and this is the part I think deserves to be stated plainly without softening, is that for any white dwarf above 1.4 solar masses, the math simply has no solution. No equilibrium exists. The radius the equations predict for a white dwarf at exactly the Chandrasekhar limit is 0. The density is infinite. These are not physical predictions exactly. They are the equations telling you they have stopped applying. The star has left the territory where white dwarf physics describes anything real. Think of it like a bridge rated for a certain load. Below the limit, the structure holds, adjusts, distributes the weight. At the limit, you are not just at the edge of safety. The bridge has no state in which it remains a bridge. Something else happens instead. In practice, a white dwarf never actually reaches the limit before something dramatic interrupts the process. The interior conditions become extreme enough, the density and temperature at the core cross their own threshold, and the carbon and oxygen that make up most white dwarfs begin to fuse, not slowly, not partially. A runaway thermonuclear reaction propagates through the entire star in seconds. The result is not a collapse, it is the opposite. A catastrophic explosion that destroys the star completely, leaves no remnant, seeds the surrounding space with iron and nickel. A Type 1, a supernova, we will get there, but for now, the limit itself is worth holding. 1.4 solar masses, a number derived on a ship, dismissed by the most respected scientist in the room, and quietly confirmed by the universe every time a white dwarf in a binary system crosses it and ceases to exist. The ceiling is real. The universe enforces it. What happens when something starts pushing a white dwarf toward it is a different kind of story entirely. Not all white dwarfs are the same thing. They arrive at roughly the same endpoint, a dense, cooling remnant and supported by electron degeneracy pressure, but what they are made of in their cores depends entirely on the star that produced them. Mass, mostly. The mass of the original star determines how far nuclear fusion proceeded before everything stopped, and how far fusion proceeded is what determines the core's composition. 3 broad types emerge from this, each one a record of a different kind of stellar life. The lightest white dwarfs have helium cores. These form from stars that were never massive enough to ignite helium fusion, stars below roughly half a solar mass, and so the remnant they leave is essentially a helium sphere, compressed and cooling. The odd thing is that single stars this light take longer than the current age of the universe to complete their evolution. So any helium core white dwarf we observe today almost certainly formed through a different route, mass transfer in a binary system where a companion star stripped away the outer layers before the full evolutionary sequence could complete. They are the product of interrupted lives. Their masses sit below about 0.45 solar masses, and they are the smallest, least dense members of the white dwarf family. The majority, and by majority something like 85 or 90% of all known white dwarfs, have carbon-oxygen cores. These form from stars that successfully fused hydrogen into helium, then helium into carbon and oxygen, but lack the mass to push further into heavier element synthesis. The Sun will produce one of these. Most of the stars you can see on a clear night will produce one of these. Carbon-oxygen white dwarfs span a wide range of masses, typically between about 0.5 and 1.2 solar masses, and they are the type that sits at the centre of almost everything interesting that happens later in this story. Then there are the oxygen-neon white dwarfs. These form from more massive progenitors, stars heavy enough to have fused carbon into oxygen and neon before losing their envelopes. Their masses typically exceed 1.2 solar masses, sometimes approaching 1.35 or higher. They are denser, more compressed, and in at least one way surprising. Current models suggest they are structurally incapable of producing Type 1a supernovae. The carbon content of the core, which is what ignites in the runaway thermonuclear explosion, is insufficient. An oxygen-neon white dwarf approaching the Chandrasekhar limit likely collapses rather than detonates, ending as a neutron star rather than an explosion. Whether this always holds is still being worked out, but the distinction matters enormously for understanding which white dwarfs are dangerous in which specific way. At the surface, white dwarfs wear a different kind of label. The spectral classification system, DA, DB, DC, and several others, describes what the outermost atmosphere contains, not the core. DA white dwarfs, the most common, show hydrogen absorption lines. Their surfaces are hydrogen-dominated, the lightest element having floated to the top under extreme gravitational settling. DB white dwarfs show helium lines instead, the hydrogen layer either absent or too thin to detect. DC white dwarfs show no lines at all. Their surface is cool enough that no element produces detectable absorption features. And then there are stranger subtypes, DZ, DQ, DAZ, each representing trace contamination from metals or carbon that have no business being there. The surface type and the core type tell different stories. A DA white dwarf could have any of the 3 core compositions beneath its hydrogen skin. The atmosphere is what the gravity has sorted to the top. The core is what the star's entire life produced. Reading one does not tell you the other. Start with your body. 70 kilograms, more or less, the rough average, the number that fits most people reading this in a chair or lying in a bed somewhere. That weight is what Earth's gravity produces from your mass. It is what you feel when you stand up, what the floor pushes back against, what makes carrying heavy things tiring. It is the only gravitational environment your body has ever known, and every instinct you have about weight, effort, and resistance was calibrated inside it. On the surface of a white dwarf, that same body would weigh approximately 7,000 tons. Not 7,000 kilograms, tons. The number is the result of surface gravity, roughly 350,000 times Earth's, applied to your mass. The figure is so far outside any biological frame of reference that it stops being weight and becomes something else. A compression, a flattening, a force that would reduce a human body to a layer thinner than a coat of paint in a fraction of a second. The word surface starts to feel like the wrong word. A threshold, maybe. A boundary condition. Young white dwarfs are hot. Extremely so. When the core is first abouts, when the planetary nebula disperses and the remnant sits bare in space, surface temperatures can exceed 100,000 degrees Celsius. Some reach higher. The star glows intensely at these temperatures, pouring out ultraviolet radiation, illuminating whatever gas surrounds it. Over billions of years, with no internal energy source replenishing what is lost, the surface cools, slowly, across timescales that make geological eras feel rushed. The oldest known white dwarfs have cooled to somewhere around 4,000 or 5,000 Kelvin, still warm, still faintly glowing, but a fraction of what they once were. The atmosphere, if you can call it that, is extraordinary in its thinness. Not thin like the upper reaches of Earth's atmosphere, where air thins gradually over hundreds of kilometers. Thin in a different way entirely. Compressed by surface gravity so intense that the entire atmospheric layer of a white dwarf may extend only tens of meters above the surface. Tens of meters. The atmosphere of a stellar object packed into something shallower than a 10-story building. What gravity does to the atmosphere, it also does to its chemistry. Elements sort themselves by weight with a brutality that no terrestrial environment approaches. Heavy elements, iron, calcium, silicon, sink, almost immediately on astronomical timescales. Hours, sometimes days. They fall below the observable surface and disappear from the spectrum. What remains at the top is the lightest available element, hydrogen, if any is present, or helium if not. This is why white dwarf atmospheres appear so chemically simple. Not because they are made of simple things, but because gravity has already sorted everything else out of sight. And this is the part I keep returning to. The surface of a white dwarf is not really a surface in any intuitive sense. A surface implies somewhere you could stand, a boundary between inside and outside, a place where conditions change from one thing to another across a distance you could cross. None of those qualities apply here. The gravitational gradient at a white dwarf's surface is so steep that the transition from near vacuum to extreme density happens across a distance measured in meters. You do not approach a white dwarf's surface the way you approach ground. You hit a wall of physics, not a place, a limit. A point past which the ordinary vocabulary of surfaces and atmospheres and temperatures begins to describe something it was never designed to describe. The numbers work, the physics is consistent, but the thing the numbers are describing does not correspond to anything the body knows how to imagine. And still, the white dwarf sits there, cooling, smaller than Earth, heavier than the sun, quiet in a way that has nothing to do with safety. A room that has been empty for years has a particular quality to it. Not cold necessarily. Temperature is not quite the right word. More like drained. The warmth that living things leave behind, the residual heat of occupation, has simply dissipated into the walls, into the air, into nothing in particular. The room is not hostile. It is just no longer holding anything it once held. A white dwarf is doing something like that. But across timescales that make the word years feel almost insulting to use in the same sentence. When the stellar core is first exposed, when the planetary nebula clears and the white dwarf sits bare in space, it is radiating intensely. Surface temperatures above 100,000 Kelvin, sometimes higher, the stored thermal energy of billions of years of stellar life bleeding outward through a surface roughly the size of Earth. There is no fusion supplementing this, no internal source generating new heat. The white dwarf is simply spending what it has, slowly, with no way to earn more. The physics of this cooling is relatively well understood. Radiation carries energy away from the surface, the interior conducts heat outward through degenerate matter, and the star dims degree by degree across timescales that are difficult to hold in the mind without losing their shape entirely. The oldest white dwarfs we have observed, the ones that formed earliest in the Milky Way's history, from the first generations of stars massive enough to end this way, are still warm, still detectable, still sitting somewhere between 4,000 and 5,000 Kelvin, faintly glowing in the infrared. The universe is approximately 13.8 billion years old. These white dwarfs have been cooling for most of that time, and they are still not done. This is worth pausing on. The entire history of complex life on Earth fits inside a window of roughly 600 million years. The dinosaurs lasted about 165 million years. Human civilization, in any recognizable form, is perhaps 10,000 years old. A white dwarf that formed when the Milky Way was young has been cooling silently and without interruption across a span that contains all of that, contains all of recorded time, all of natural history, all of geological time, and still retains enough heat to register on our instruments. The cooling is real, the progress is measurable, it is just happening on a clock that does not care about any of the clocks we use. The theoretical endpoint of this process is called a black dwarf. A white dwarf cooled completely, temperature approaching absolute zero, no longer emitting detectable radiation, a dark crystalline sphere of carbon and oxygen supported by electron degeneracy pressure, invisible against the backdrop of space. This is what white dwarfs are becoming. This is where the long cooling sequence eventually leads, if given enough time. The amount of time required is approximately 10 to the power of 15 years, a quadrillion years, give or take. The current age of the universe is 13.8 billion, roughly 1.38 times 10 to the power of 10. The cooling time required to produce a black dwarf is roughly 100,000 times longer than the universe has currently existed. And this means something specific, something that takes a moment to fully register. No black dwarf exists anywhere. Not one. The universe has not had time to produce a single one. Every white dwarf that has ever formed, every stellar remnant from every star that completed its evolution across the entire history of the observable universe, is still, right now, somewhere on the cooling curve. Still warm, still radiating, still in the process of becoming something the universe has not yet had time to make. The dark is coming, just slowly. Across a silence so long that even the dying of stars is only the beginning of it. Something, though, interrupts the cooling for some of them. Not the dark, something stranger, something internal. And it delays the inevitable in ways that took us entirely by surprise. Freezing is usually thought of as something that happens quickly. Water in a cold enough environment, ice forming at the edges of a glass left outside, spreading inward, the liquid surrendering its motion gradually until there is no motion left. The process is familiar enough that it rarely seems strange. But freezing inside a white dwarf is a different kind of event entirely. Slower, more internal, something the star does not announce, and that took astronomers a surprisingly long time to confirm was happening at all. As a white dwarf cools, the carbon and oxygen ions in its interior, the nuclei, positively charged, enormous relative to the electrons flowing around them, begin to slow. At the temperatures present in a young white dwarf, these ions move freely, jostling past each other in a dense, hot fluid. A quantum liquid, technically, though the word liquid carries connotations of something thin and loose that do not quite fit matter at 1,000,000 times the density of water. As cooling continues, the ions lose thermal energy. Their motion becomes less random, and at a specific threshold temperature, dependent on the composition and the density, they stop being a disordered fluid and begin locking into a regular lattice. A crystal structure. Solid, ordered, fixed in geometric arrangement. The electrons, importantly, do not freeze. They keep moving, keep conducting. The crystalline lattice of ions forms within a sea of freely flowing degenerate electrons, which is why this material conducts heat efficiently even in its solid state, and why the cooling continues after crystallization rather than stopping. What crystallizes is the ionic skeleton of the star, not the entire interior. The electrons carry on, indifferent. Now here is the part that took time to appreciate. When a substance freezes, any substance, water or wax or the interior of a white dwarf, it releases latent heat. The transition from disordered to ordered releases energy. The same energy that was required to maintain the disordered state. In water, this latent heat is small enough that you would not notice it without instruments. In a white dwarf core, where the mass involved is a significant fraction of a solar mass, the latent heat released during crystallization is substantial, enough to slow the cooling measurably. The white dwarf is freezing, and the freezing itself is keeping it warmer than it would otherwise be, by roughly 1 billion years. 1 billion years of additional warmth, produced not by fusion, not by accretion, but by the act of becoming solid. In 2019, astronomers using data from the Gaia Space Telescope found something in the white dwarf population that crystallization theory had predicted, but nobody had yet cleanly confirmed. In the color magnitude diagrams, the plot of luminosity against temperature for a large sample of white dwarfs, there was a pileup, a clustering of white dwarfs in a region where, based on standard cooling models, they should have been passing through more quickly. Too many stars lingering at a particular temperature, a particular brightness. Like a crowd backed up at a door that's taking longer to open than expected. This clustering is called the Q branch. The white dwarfs caught there are not defective, not unusual in any individual way. They are simply mid-crystallization, held at a nearly constant luminosity while the latent heat from their freezing interiors bleeds slowly outward. The cooling has paused, not stopped, but stretched, and as a result is a statistical fingerprint in the population. Hundreds of thousands of white dwarfs, all caught in the same slow moment, visible only because Gaia could observe enough of them simultaneously to make the pile-up statistically undeniable. The observation confirmed something that had been theorized for decades. Not just that white dwarfs crystallize, but that the crystallization matters. That it changes the cooling timeline in ways large enough to leave a mark on the observable distribution of an entire stellar population. Dying slower, it turns out, is not a failure of the process. It is a property of the material. The star is not clinging to warmth out of something as imprecise as reluctance. It is obeying thermodynamics, releasing the energy stored in the difference between disorder and order, paying out one last reserve before the long descent resumes. And somewhere inside that reserve, something else is being set in motion. Something the cooling itself is generating quietly in the conducting fluid surrounding the growing crystal. As the crystal grows outward from the center of a cooling white dwarf, the ions joining the lattice are not joining in equal proportion. Oxygen, heavier and more chemically compatible with the crystalline structure forming under these conditions, preferentially locks into the solid. Carbon, lighter and less accommodating, tends to remain behind in the surrounding liquid layer. This separation is not dramatic. It happens slowly, incrementally, across millions of years. But it is real, and it is consistent, and it produces something the white dwarf's interior had not contained before, a compositional gradient, a liquid layer above a growing solid enriched in carbon relative to what it once was, sitting above a crystal enriched in oxygen relative to what it once was. Density differences drive motion. The carbon-enriched liquid above the crystallization front is slightly buoyant compared to the material around it, and it rises. Cooler, oxygen-depleted material sinks. The interior begins to convect, not violently, not quickly, but persistently in a slow circulation driven by nothing more exotic than the same principle that moves warm air toward a ceiling. and the fluid convecting is not neutral. It is a dense, hot plasma of ions and freely flowing electrons, electrically conducting, rotating, because the white dwarf as a whole is rotating. The conditions are, in other words, exactly what you need to run a dynamo. A dynamo is simply a conducting fluid in motion, curved by rotation, generating a magnetic field. Earth has one, the convecting liquid iron in its outer core, producing the magnetic field that deflects solar wind and orients compasses. The scale is different in a white dwarf, and the material is different, and the driving mechanism is different. But the principle is the same slow engine, conducting fluid moving in a rotating system, coiling and amplifying magnetic field lines over time until the field becomes strong enough to measure at the surface. Some models suggest fields of up to a megagauss or more could emerge from this process alone. I want to pause here for a moment. The Patreon for this channel, The Sleepy Physicist, is where the full research notes for every episode live, over 50 episodes, audio content, comparison files, and the detailed sourced documents that sit behind what you are hearing right now. Alison, who has been with this project longer than almost anyone, and Matthew M. and Brian Winter, whose support has been genuinely steadying, thank you. To everyone else contributing, this runs because of you. The link is in the description if you want to be part of it. The timing of magnetic field emergence is, in its own way, evidence for the dynamo mechanism. Most magnetic white dwarfs are not young. They appear predominantly in the cooler, older portion of the white dwarf population, exactly where crystallization is expected to be well underway. If magnetism were purely inherited from the progenitor star, a fossil field carried through from the main sequence, you might expect to see it distributed more evenly across white dwarf ages. The late appearance suggests something is generating the field during the white dwarf phase itself. At the moment, the interior conditions become right for a dynamo to operate. But the picture is not entirely clean, and it is worth saying that plainly. Recent observations, from 20 to 24 and 20 to 25 particularly, have complicated the straightforward crystallization dynamo story. Some magnetic white dwarfs appear too early in their cooling for crystallization to have progressed far enough to drive significant convection. Some ultramassive white dwarfs show magnetic fields that seem stronger and earlier than dynamo models comfortably predict. An alternative, or perhaps complementary explanation, is that some fields are indeed fossil remnants, buried deep in the white dwarf during formation, slowly diffusing outward through the degenerate interior over billions of years until they finally reach the surface and become observable. The diffusion timescales involved are long and billions of years in some models, which means a fossil field originating in the progenitor star's convective core might not reach the white dwarf's surface until the star has already cooled into the temperature range where crystallization is also underway. The two mechanisms arrive at the same moment in the cooling life of the star, producing the same observational signature, a magnetic field appearing late, through different physical routes. Separating them requires more than timing. It requires measuring field strengths, comparing them against what each mechanism predicts for white dwarfs of different masses and compositions, and building a population picture large enough to distinguish the two contributions statistically. That picture is still being assembled. The 2025 and 2026 observations have added objects that complicate both stories simultaneously, some that fit the crystallization dynamo, some that fit fossil field diffusion, and some that fit neither cleanly. The honest position, at this moment, is that both mechanisms are probably real, and that which one dominates likely depends on the white dwarf's mass, composition, and evolutionary history. A single explanation may never fully account for the observed magnetic white dwarf population. What is not in doubt is that the magnetism is there, and that it emerges. A white dwarf that showed no detectable magnetic field for billions of years can develop one. The interior is not static. The crystallization is not simply a cooling delay. It is a structural and electromagnetic event, producing something new in the star's outer layers that was not present before the freezing began. Whether the dynamo generates the field or the freezing merely carries an old one to the surface, the result is the same. An object that looks finished, that looks as though everything that was going to happen to it already has, quietly producing a magnetic field strong enough to measurably alter the spectra of atoms in its atmosphere. Dead things do not do that. Press your ear against a wall. If something is moving on the other side, or water in a pipe, footsteps, a low vibration, you can sometimes sense the interior of a structure you cannot see, not perfectly, not with detail, but the wall transmits something. The motion inside reaches the surface, and if you are paying close enough attention, you can begin to read it. Some white dwarfs are doing something like that, broadcasting their interiors through vibration. Not because they're trying to, there is no intent here, just physics, but because under certain conditions, the outer layers of a white dwarf become unstable in a specific structured way, and the star begins to pulse. These are called ZZ Ceti stars, or DAV white dwarfs. The names refer to the same class of object, the ZZ Ceti designation, coming from the prototype star in the Corona Australis constellation, where this behaviour was first identified. They are hydrogen atmosphere white dwarfs that have cooled into a particular temperature range, roughly between 10,500 and 12,500 Kelvin, where the hydrogen in the outer layers reaches a state of partial ionization. Partially ionized hydrogen has a tendency to trap radiation rather than let it pass through smoothly. The trapped energy builds, pushes outward, overshoots, falls back, oscillates. The white dwarf does not expand or contract as a whole. It vibrates non-radially, different parts of its surface moving in and out of phase with each other in complex geometric patterns. The periods of these oscillations run from a few minutes to around 20 minutes depending on the star. The bell comparison is easy to reach for here. A struck bell rings at frequencies determined by its size, its shape, its composition, its internal structure. Two bells that look identical from the outside might ring differently if their alloys differ, or if one has an internal crack, or if the wall thickness varies in a way you cannot see. The frequencies encode the structure, and a ZZ Ceti star does something similar, except nobody struck it, and the ringing has been going on, in some cases, for longer than human civilization has existed. Asteroseismology is the science of reading that ringing. By measuring the precise frequencies at which a white dwarf oscillates, which periods are present, which are absent, how the modes relate to each other mathematically, astronomers can work backwards to the internal structure that would produce exactly those frequencies. It is an inverse problem. Given the output, reconstruct the source. The mathematics involved is involved, and the solutions are not always unique, but the constraints it places on the interior structure are genuinely beyond what any other method can provide. What can be extracted from a well-studied pulsating white dwarf is specific enough to be worth listing plainly. The thickness of the hydrogen layer at the surface, which varies between white dwarfs and affects their long-term evolution. The carbon-to-oxygen ratio in the core, which determines the star's behaviour if it ever approaches the Chandrasekhar limit. The rotation rate of the interior, which the pulsation modes split in ways that carry rotational information. The presence and approximate strength of a magnetic field, which distorts the mode frequencies in characteristic ways. These are properties of the deep interior, invisible to any telescope, inaccessible by any direct observation. Nearly 500 DAV pulsators have now been identified. That number is growing. Surveys like TESS have been particularly productive, catching the brightness variations of faint white dwarfs across wide areas of sky. Each new ZZ Ceti star is another interior made partially legible, another set of frequencies to decode. And this is the part that sits with me a little. The star is not communicating, not in any meaningful sense, but it is transmitting. The trembling at its surface is a physical consequence of its internal structure, carried outward through the same layers that block every other form of observation. We cannot see inside a white dwarf. We can listen, though. Nearly 500 of them quietly ringing in the dark. An isolated white dwarf is, in every meaningful sense, just cooling. No fusion, no accretion, no interaction with anything beyond the slow radiation of stored heat into the surrounding space. Left alone, it follows a single trajectory, a dimmer, cooler, quieter, across timescales that eventually become geological, then cosmological, then something beyond any scale we have names for. An isolated white dwarf is not threatening. It is, if anything, the opposite, a stellar remnant doing the most passive thing a massive object can do. But a significant fraction of stars form in binary systems. Two stars orbiting a common centre of mass, gravitationally bound, evolving on parallel timescales that sometimes diverge in consequential ways. The more massive star in a binary evolves faster, burns through its fuel more quickly, expands into a red giant, sheds its outer layers, becomes a white dwarf first. The companion star, meanwhile, continues its own main sequence life, sometimes for billions of years afterward. And if the orbital separation is close enough, a few solar radii, sometimes less, something eventually happens. The companion star grows. As it ages, it too begins to exhaust its hydrogen, its core contracts, its outer layers expand. A red giant expanding inside a tight binary orbit does not expand freely in all directions. Gravity from the white dwarf shapes the space around the system in a way that creates, at a specific point between the two stars, a gravitational boundary. The point where the companion's own gravity and the white dwarf's gravity balance exactly. This boundary, the inner Lagrange point, sitting within a teardrop-shaped volume called the Roche lobe, becomes critical when the expanding companion star fills its rear lobe completely. At that point, any further expansion means material at the companion's surface is no longer bound to the companion. It flows, not explosively, not as an eruption, it simply crosses the boundary and falls toward the white dwarf, following the gravitational gradient that now slopes inward toward the denser object. This flow of material does not fall directly onto the white dwarf. It carries angular momentum from the companion star's orbit, and this momentum causes it to spiral inward rather than plunge straight down, spreading into a flattened rotating disk of gas around the white dwarf, an accretion disk. It sits there, orbiting, its inner edge close to the white dwarf's surface, the material slowly losing energy through friction and radiation as it spirals inward. The disk is hot, bright in X-rays often, visible from other galaxies, in some cases, because the energy released by infalling material can be substantial, but the disk itself is not the concern here. The disk is the delivery mechanism. What the disk delivers slowly and continuously is hydrogen. Hydrogen stripped from the companion star, processed through the disk, arriving at the white dwarf's surface in a steady, patient accumulation, layer by layer, year by year. The white dwarf's gravity compresses each new arrival against what came before. The surface hydrogen layer grows thicker, denser, hotter at its base as the weight of everything above presses down on it. And here is the part that I find difficult to look away from. The white dwarf has no mechanism to return this mass. It cannot shed it. It cannot burn it yet, not in any sustained way. Electron degeneracy pressure does not care about temperature. The star does not expand to relieve the increasing load the way a normal star would. It just accepts the mass, compresses further, grows slightly smaller as it grows heavier. Every gram of hydrogen that arrives from the companion star becomes a permanent addition to the white dwarf's total mass, until something happens to interrupt the process. The trap is not dramatic. It does not announce itself. A white dwarf in a close binary system is simply accumulating solely, inexorably, without release, mass it will never willingly give back, mass that is walking it increment by increment toward a number. That number again, the one derived on a ship in 1930, the one the universe enforces without exception. What happens before that number is reached is already extraordinary. What happens on the surface of a white dwarf under the weight of all that accumulated hydrogen is its own event entirely, and it does not wait for the limit to arrive. For decades, sometimes centuries, nothing visible happens. The accretion disk feeds its steady supply of hydrogen to the white dwarf's surface, and the surface accepts it quietly, each new layer compressed against the last by gravity 350,000 times Earth's. The hydrogen does not ignite immediately. It cannot. Not yet. The temperature at the base of the accreted layer is not high enough. The pressure is building, but building slowly, the way a room fills with something you cannot see until the moment you notice it has become difficult to breathe. The compression does the work that time alone cannot. As the hydrogen layer thickens, the weight of everything above bears down on the base with increasing force. Under that force, the density at the base climbs. The temperature climbs with it, not because anything is being added from outside, but because compression itself generates heat, and degenerate matter conducts that heat differently than ordinary gas would. In a normal stellar environment, rising temperature causes expansion, which relieves pressure, which moderates temperature, a natural thermostat. But the hydrogen sitting on a white dwarf surface is not degenerate in the same way the core is. It behaves more like ordinary gas, and ordinary gas under these conditions has no thermostat. The temperature rises, the pressure rises with it, the fusion rate climbs, and the climbing fusion rate generates more heat, which raises the temperature further, which raises the fusion rate again. This is a thermonuclear runaway. Once it begins, it does not moderate. The reaction accelerates beyond any natural check, releasing energy faster than the surrounding material can absorb or redistribute it. The base of the hydrogen layer reaches temperatures of tens of millions of degrees in a matter of seconds. The energy propagates outward through the accumulated shell. What was moments before a quiet layer of compressed hydrogen becomes a detonating envelope, expanding violently outward from the white dwarf surface at velocities that can reach several thousand kilometers per second. The brightness increases, and the number here is the point, not any adjective around it, up to 19 magnitudes. In astronomy, a difference of 5 magnitudes corresponds to a factor of 100 in brightness. 19 magnitudes is a factor approaching 40 million. A system that was invisible to the naked eye can, during a nova outburst, become one of the brightest objects in the night sky, visible in daylight in extreme cases, drawing the attention of astronomers and the general public before anyone knows quite what they are looking at. The ejected shell of material expands outward at its thousands of kilometers per second, glowing as it goes, thinning over weeks and months until it disperses into the surrounding space, and the white dwarf survives. This is the part that takes a moment. The explosion, an event energetic enough to produce a 40 million-fold increase in brightness, enough to eject material at a fraction of a percent of the speed of light, does not destroy the white dwarf, does not significantly alter its structure, does not remove its core mass. The detonating layer was the accreted hydrogen envelope sitting on the surface. The white dwarf beneath was never at risk in any structural sense. After the ejector disperses, what remains is the white dwarf, essentially unchanged, the accretion disk beginning to reform around it, the companion star continuing to shed material across the Roche-Lobe boundary. Is that really what just happened? An explosion that could be seen across thousands of light years, and the object at its center is simply still there, cooling, waiting? The answer is yes. And the consequence of that answer is what makes Novae genuinely strange in a way the explosion itself almost distracts from. The surface has been cleared. The accreted hydrogen, the layer that built for decades or centuries, is gone, ejected into space. The white dwarf's surface is clean again, and the accretion disk, patient and indifferent to what just occurred, begins delivering hydrogen to that clean surface immediately. The process resumes. The layer begins building again. The pressure begins climbing again. The clock, which just reached zero and released everything it had accumulated, flips. The countdown restarts, not as a metaphor for something ominous, just as a description of what physically happens next. The white dwarf did not die. It reset. And a system that resets is not finished. It is simply between events, a accumulating toward the next one, the same way it accumulated toward the last. Some systems do this once in recorded history, others do it on timescales short enough for humans to observe multiple cycles. What the recurrence rate tells us about those systems is its own kind of information. About 2,630 light-years from Earth, in the constellation Corona Borealis, there is a binary system that has been observed erupting twice in recorded history, once in 1866, once in 1946, and is, by most current assessments, overdue for a third. The system is called T Coronae Borealis, TCRB in the shorthand. It contains a white dwarf of approximately 1.35 solar masses orbiting a red giant companion, the two locked in an orbital period of roughly 228 days, the red giant feeding material steadily across the boundary between them. On average, the hydrogen accumulates for around 80 years before the surface ignites. The system then brightens to roughly second magnitude, visible to the naked eye, prominent in the night sky, and fades again over the following weeks. Then the clock, as it were, resets. In 2023, something changed. TCRB, which had been gradually brightening in the years prior, a pattern also observed before the 1946 eruption, suddenly dimmed. Not dramatically, not catastrophically, just a quiet dip in brightness that matched almost precisely the behaviour the system displayed roughly a year before its last eruption. Astronomers noted it. Predictions were made. The eruption was anticipated sometime in 2024 or 2025. The system has been watched closely since, by professionals and amateurs both, a collective attention directed at a point of light that most people would struggle to locate in an unfamiliar part of the sky. What a recurrence timescale tells you about a system is specific. A nova that repeats every 80 years is different in its internal logic from one that repeats every 10,000 years or one that has only erupted once in all of recorded observation. Short recurrence times require two things simultaneously: a white dwarf massive enough that it needs less accumulated hydrogen to reach the ignition threshold, and an accretion rate high enough to reach that threshold quickly. The more massive the white dwarf, the higher the surface gravity, the less hydrogen required to build the pressure needed for runaway. The faster the accretion, the sooner that threshold arrives. TCRB satisfies both conditions. The 1.35 solar mass white dwarf at its centre is one of the most massive known in any recurrent nova system, sitting 0.05 solar masses below the Chandrasekhar limit. That proximity is not incidental. It is the explanation for the 80-year clock. And this is where the arithmetic becomes, I am not sure unsettling is quite the right word, but it is close. A nova explosion ejects the accreted hydrogen envelope, but not all of it. Some fraction of the accreted material is not ejected, it is retained, mixed into the white dwarf's outer layers, incrementally increasing the total mass of the star. The exact fraction varies by system, by accretion rate, by white dwarf mass. It is not always a net gain. Some models suggest certain systems actually lose mass per cycle, ejecting slightly more than they accrete when a white dwarf material is mixed into the ejector. But for systems like TCRB, high mass, high accretion rate, short recurrence, the current evidence leans toward net mass accumulation per cycle. Each eruption clears the surface. Each new cycle deposits material. The white dwarf, cycle by cycle, may be growing, slowly, incrementally, by amounts that are difficult to measure directly and debated in the literature, but growing. A white dwarf at 1.35 solar masses needs to gain 0.05 solar masses to reach the Chandrasekhar limit. That is not nothing, it is a meaningful fraction of the Sun's mass. Across many nova cycles, each depositing a small net gain, the timescale for accumulating that 0.05 solar masses could be millions or tens of millions of years. Long by any human measure, not long by stellar measure. Some recurrent novae may be walking quietly and without announcement toward a threshold from which there is no reset. Not a surface explosion that clears the clock and starts again. Something that goes all the way through. What that looks like, What happens when the accumulation does not stop at the surface is where this goes next. Mass arrives the way it always has, through the accretion disk, through the slow spiral of hydrogen from a companion star giving up material it cannot hold against the white dwarf's gravitational pull, gram by gram, year by year. The surface processes whatever arrives, sometimes explosively, in the Nova cycle already described, clearing the deck and beginning again. But the net direction for the right kind of system is upward. The total mass of the white dwarf increases, not quickly, not perceptibly on any timescale a human life could span, but the number climbs, and as it climbs, the white dwarf shrinks. This is the inverse mass-radius relationship asserting itself again, but with a different weight now that the context has changed. When a white dwarf's mass increases, the additional gravity compresses the interior further. The electrons, already filling every available quantum state, are forced into smaller volumes. The star does not expand to accommodate the new mass the way a normal star would, it contracts. A white dwarf at 0.8 solar masses sits at roughly the radius of Earth. One approaching 1.2 solar masses is measurably smaller. One at 1.3 solar masses smaller still. The shrinking is real, continuous, and in a precise mathematical sense, points towards zero. At the centre, the density climbs. This is not a metaphor for something extreme, it is a measurable physical quantity, and in the most massive white dwarfs known, the central density approaches values on the order of 10 to the 10th power grams per cubic centimetre. A cubic centimetre of core material weighing 10 billion grams. The number is large enough that it stops corresponding to anything tactile, but the consequences of that density are tactile in their way. The electrons packed into that space have no room left in the lower energy states. Every state up to the Fermi level is occupied. The electrons sit as tightly as quantum mechanics allows. To maintain their exclusion from each other under this compression, they must occupy high energy states, and high energy states at these densities mean high velocities. The electrons in the core of a white dwarf approaching the Chandrasekhar limit are not moving at the modest fractions of the speed of light seen in lower mass white dwarfs. They are moving at velocities where relativistic effects become significant, where the relationship between momentum and energy changes, where the standard equations for degeneracy pressure, derived assuming non-relativistic electrons, begin to give way to relativistic corrections that tell a different story. The story they tell is this. Relativistic electrons generate degeneracy pressure that increases more slowly with density than non-relativistic electrons do. The pressure is still there, the wall is still there, but the wall is no longer keeping pace with the gravitational demand being placed on it. Each new increment of mass adds more gravitational force than the corresponding increase in degeneracy pressure can offset. The margin, the difference between what gravity demands and what the electrons can provide, begins to close. This happens silently. The white dwarf does not change its appearance in any way that would signal what is occurring internally. It glows at whatever temperature its cooling has brought it to. It maintains its orbit around its companion. It accepts accreted material and processes it through Nova cycles if conditions allow. From outside it is simply a white dwarf, smaller than average for its mass, denser than most, but nothing about its surface broadcasts the internal arithmetic. Thresholds do not announce themselves, not this kind. The kind where the structure that has held for billions of years is still holding, right up to the point where it is not, where the margin closes not to a small number but to zero, where the equations that described a stable object stop having a stable solution. The star becomes smaller, denser, the electrons faster, the pressure less adequate, the gap between gravitational demand and quantum resistance narrower, quieter. Not metaphorically quieter. The white dwarf was always quiet, radiating in whatever wavelengths its temperature produced, orbiting, accumulating. But something about the approach to this threshold has a specific quality. A structure under load that has not yet failed feels different from one with comfortable margin. The silence is the same, the stillness looks the same, what follows does not. At some point, not announced, not preceded by any observable warning at the surface, The conditions at the center of the white dwarf cross a threshold. The density and temperature in the core reach the point where carbon fusion ignites, not at the surface where hydrogen burns during nova cycles, not in a shell where helium might accumulate and flash, at the center, in the carbon-oxygen material that has been the white dwarf's core since the day it formed, the material that has sat inert for millions or billions of years, waiting under conditions that never previously reached the ignition point. The fusion begins in a region smaller than a city, a hot spot or several forming in the dense core and immediately beginning to spread. The burning front moves outward through the star as a deflagration, a subsonic flame in the technical sense, propagating through the carbon-oxygen interior by heating the material ahead of it to ignition temperature. The flame moves quickly by any ordinary standard. By the standard of what is about to happen, it is almost slow. The deflagration churns through the interior, releasing energy, expanding the outer layers slightly, the star beginning to swell in the first fraction of a second after ignition. Then the flame front, under conditions that theorists have been working to precisely characterize for decades, transitions. The deflagration becomes a detonation. The burning front accelerates past the speed of sound in the stellar material, driving a shockwave ahead of it, compressing and igniting material faster than it can respond hydrodynamically. The detonation moves through the remaining unburned carbon and oxygen in milliseconds. The entire interior of the white dwarf, a star that has existed in some cases for billions of years, is consumed in a time measured in seconds. The energy released is approximately 1 to 2 times 10 to the 44th power joules. The Sun will emit, across its entire 10 billion year main sequence lifetime, roughly 10 to the 44th power joules in total. A Type 1. A supernova releases that much in seconds. The comparison is not offered for drama, it is offered because the scale is genuinely difficult to place without it, and even with it, the number sits at the edge of what the mind can do anything useful with. The outer layers of the white dwarf, driven by this energy release, accelerate outward. The ejector reaches velocities of roughly 10,000 to 20,000 kilometers per second and several percent of the speed of light. The expanding shell is not uniform. The physics of the deflagration to detonation transition produces asymmetries, layers of different composition moving at different velocities, the whole structure evolving as it expands and cools, and the radioactive nickel-56 at its core decays to cobalt and then to iron, releasing gamma rays that power the light curve for weeks after the initial explosion, and nothing survives. This is the part I keep returning to, because it is genuinely unlike almost everything else that happens in stellar evolution. A core collapse supernova, the death of a massive star, leaves a neutron star or a black hole, something, a remnant that carries the memory of what the star was, a Type 1. A supernova leaves nothing. The white dwarf that existed, that had been cooling for millions of years, accumulating mass from its companion, surviving nova cycles, approaching the limit increment by increment, is completely gone. Not collapsed into something denser, not scattered with a core remaining, gone. The electron degeneracy pressure that held it together is irrelevant now. There is no longer a structure for it to hold. The entire mass of the star, sir, has been converted to kinetic energy and radiation, an expanding ejector. What the ejector contains is worth noting. Iron, nickel, intermediate mass elements, silicon, sulfur, calcium, argon, produced in the nuclear burning as heavier elements were synthesized in the seconds of the explosion. A typical Type 1. A supernova produces roughly half a solar mass of nickel-56 alone, which decays over weeks into the iron that makes up a significant fraction of the heavy element content of the universe. The iron in your blood has a provenance. Some of it, not all, but some, was synthesized in the seconds of a Type 1 supernova and scattered across the interstellar medium billions of years before the solar system formed. The companion star, if one existed, survives. thrown outward by the sudden loss of the gravitational mass it was orbiting, moving now at whatever velocity the orbital mechanics impart to it, a runaway star carrying the kinetic memory of a system that no longer exists. Evidence of this has been found. Stars moving at anomalous velocities, their trajectories tracing back to the locations of historical supernovae. The white dwarf is simply not there anymore. Where it was, an expanding shell of iron and nickel and energy moves outward at several % of the speed of light, growing, thinning, cooling, eventually merging with the interstellar medium over thousands of years. The remnant is not the star. The remnant is what the star became in its final seconds, moving away from a centre that no longer contains anything, just absence, expanding. The scenario described in the previous chapter, a white dwarf accreting hydrogen from a companion star, mass climbing toward the Chandrasekhar limit, carbon igniting at the core, is one route to a Type 1a supernova. It is not the only one. The universe has found at least 2 other ways to reach the same endpoint, and both of them operate without requiring the white dwarf to approach 1.4 solar masses. Both can occur in the apparent absence of any warning. Both leave the same expanding shell of iron and nickel moving outward through space at thousands of kilometers per second. The first alternative begins with helium. In certain binary configurations, a white dwarf accretes not hydrogen but helium, stripped from a helium-rich companion or accumulated gametes, as a hydrogen accreted earlier is processed into helium at the white dwarf's surface. Helium does not sit as quietly as hydrogen under compression. It ignites at lower pressures and temperatures, and a helium shell of sufficient mass can detonate before the white dwarf's total mass approaches any critical threshold. The shell, sitting above the carbon-oxygen core, thickening over time, reaches conditions where helium fusion ignites explosively across its surface. The detonation sends energy in 2 directions, outward, into space producing the initial blast, and inward. The shock wave from the helium detonation converges toward the center of the white dwarf, compressing the carbon-oxygen core as it travels. The compression is not gentle. It raises the density and temperature in the core rapidly, and if the shockwave is strong enough, if the white dwarf is massive enough, the core reaches carbon ignition conditions before the shockwave passes through. A second detonation begins, this time in the core, propagating outward through the star, while the helium detonation is still expanding above it. 2 detonations, one triggered by the other. The white dwarf, which may have been significantly below the Chandrasekhar limit when this began, perhaps 0.8 or 0.9 solar masses, is consumed from both inside and outside simultaneously. What remains is identical in broad character to a standard Type 1. A. An expanding shell of synthesized elements. No remnant. The companion star, if present, thrown outward by the sudden gravitational change. The double detonation mechanism is currently one of the leading candidates for explaining a subset of Type 1a supernovae, particularly the subluminous ones, which produce less nickel-56 than the classical Chandrasekhar mass explosion, and have for years resisted clean explanation. The second alternative requires no companion star at all. 2 white dwarfs, orbiting each other in a close binary, both remnants of stars that completed their evolution, cooling side by side in an orbit that is, very slowly, shrinking. The mechanism driving the shrinkage is gravitational wave emission. 2 massive objects orbiting each other accelerate the space-time around them in a pattern that carries energy away from the system as gravitational radiation. The energy loss is tiny per orbit, immeasurably small on human timescales for most systems, but it is continuous, and it accumulates. Over millions or billions of years, the orbital separation decreases, the orbital period shortens, the 2 white dwarfs move closer. At some point, the separation becomes small enough that the gravitational field of the more massive white dwarf begins to tidally distort the less massive one. The distortion grows as the orbit tightens further. The less massive white dwarf is stretched, pulled, its outer layers drawn toward its companion. Eventually, the transition from stable binary to disruption can happen quickly once tidal forces become significant. The less massive white dwarf is disrupted entirely, its material streaming onto and around the more massive one. If their combined mass exceeds the Chandrasekhar limit, or if the double detonation mechanism triggers in the resulting configuration, the system detonates. Neither pathway announces itself. No brightening beforehand, no detectable precursor at the surface of the white dwarf, no signal that something is about to change. The helium shell builds in sonce. The gravitational waves carry energy away in sorens, the orbit shrinks in solens, and then, in seconds, a star that existed for billions of years does not exist anymore. The silence is not incidental, it is structural. These are mechanisms that operate below any threshold of external observation until the moment they produce the largest class of stellar explosion in the observable universe. Something nearby would simply see the sky change. In April 2025, a paper appeared in Nature Astronomy describing a binary star system that had been characterized in enough detail to make a specific prediction about its future. The system's full designation is WDJ 181058.67 plus 3 11940.94. It contains two white dwarfs orbiting each other with a period of 14.24 hours, their separation close enough that gravitational wave emission is measurably draining energy from the orbit. The system is located 49 parsecs from Earth, roughly 160 light-years. In galactic terms, this is the next street over. The two white dwarfs are not identical. The more massive of the pair sits at approximately 0.9 solar masses, the less massive at around 0.6. Combined, they total 1.555 solar masses, a number that clears the Chandrasekhar limit by 0.155 solar masses with room to spare. Neither white dwarf individually is close to the limit, but the limit applies to what they will eventually become together, and what they will become together is determined by a process already underway and impossible to stop. Gravitational wave emission is continuous. The orbit is shrinking. Not quickly, the current rate of inspiral is far below anything detectable without careful long baseline measurement, but the direction is fixed. The two white dwarfs are moving toward each other, their orbital period shortening by amounts that accumulate meaningfully only across millions of years. The calculation of when they will merge is straightforward given the measured parameters of the system. 22.6 billion years, plus or minus about a billion. Longer than the current age of the universe. Longer than the sun's remaining lifetime, longer than most timescales that appear in astrophysics discussions without causing people to simply stop tracking the number. And yet the number is not the point. Or rather, it is not the most important point. The most important point is the 49 parsecs. This is what I keep returning to when I think about this system. The future is abstract. 22 billion years is not a time frame that connects to anything in human experience, and it would be dishonest to pretend the detonation feels imminent just because the system exists. It does not feel imminent. It is not imminent. But the system itself, the two white dwarfs orbiting each other every 14 hours, draining their orbit of energy with every pass, carrying a combined mass that guarantees their eventual merger ends in complete detonation, that system exists right now, tonight, at 160 light-years, in the same galactic neighborhood where the sun has been sitting for 4.5 billion years. It is not a theoretical construct or a statistical prediction about some distant population. It is a specific object with a specific address and a specific fate already written into its orbital mechanics. When it eventually detonates, in whatever configuration the double detonation mechanism or the merger dynamics produce, the event will be visible from Earth. The predicted apparent magnitude is approximately -16. For reference, the full moon reaches about -13. Venus at its brightest manages around -5, A magnitude of -16 would make WDJ 181058 briefly the brightest object in the night sky by a factor that strains any comparison the solar system offers. 200,000 times brighter than Jupiter, visible in daylight, casting shadows at night if anyone is standing outside on a clear night 22.6 billion years from now to notice. The companion star in this system, if either white dwarf has a surviving companion by the time of detonation which is unclear, will be thrown outward at whatever velocity the orbital mechanics impart. No remnant of the white dwarfs will remain. The expanding shell of iron and nickel will move outward and eventually thin into the interstellar medium, as it always does. The space where the system currently sits will be empty, and before any of that, it is there now, orbiting, the period ticking over every 14.24 hours, the gravitational waves carrying their tiny tacks of energy away from the system with every revolution. The combined mass of 1.555 solar masses sitting above the limit that Chandrasekhar worked out on a ship in 1930, in a system that the universe has not yet had time to detonate. That is what makes it worth naming, not the explosion to come, the waiting. Already in progress. If you know how bright something actually is, its true luminosity, independent of distance, then how bright it appears from where you are standing tells you how far away it is. A candle at 1 meter looks a certain brightness. The same candle at 10 meters looks dimmer by a precise calculable amount. At 100 meters, dimmer still, by the same inverse square relationship. The logic is ancient, and it works for anything whose intrinsic brightness you can pin down with confidence. The difficulty, in cosmology, has always been finding objects bright enough to see at the distances that matter, and consistent enough in their intrinsic luminosity that the apparent brightness comparison is meaningful. Type 1. A supernovae are, to a useful approximation, consistent. The reason traces back to the Chandrasekhar limit. If a Type 1 supernova occurs when a white dwarf's mass approaches 1.4 solar masses, the same threshold for every white dwarf, everywhere in the universe, because the physics of relativistic electron degeneracy pressure does not vary with location, then the total mass of the exploding object is similar from one event to the next. Similar mass, similar composition, similar energy release, similar peak brightness, not identical, there are variations and the field has spent decades characterizing them, but similar enough that applying a correction based on the shape of the light curve, how quickly the supernova brightens and fades, reduces the scatter in peak brightness to something manageable. A standard candle, imperfect but usable, bright enough to see across billions of light years, consistent enough to compare. In the late 1990s, 2 independent teams set out to use Type 1 supernovae to measure the expansion history of the universe. The Supernova Cosmology Project, led by Saul Perlmutter, and the High-Z Supernova Search Team, led by Brian Schmidt and Adam Rees. Both groups were doing essentially the same thing, finding Type 1 supernovae at high redshifts, far enough away that the light had been travelling for billions of years, and comparing their apparent brightness to what the standard candle relationship predicted. The comparison would reveal how fast the universe was expanding when that light was emitted, and by looking at supernovae at different distances, how the expansion rate had changed over time. The expectation shared by essentially everyone working in cosmology at the time, was that the expansion would be decelerating. The universe was full of matter, and matter gravitates, and gravity should be slowing the expansion that began at the Big Bang. The data would confirm the deceleration and help pin down exactly how much matter the universe contained. The data did not show deceleration. The distant supernovae were fainter than they should have been, not by an amount that suggested measurement error, by an amount that once the teams had checked and rechecked their analysis, pointed consistently in one direction. The universe's expansion was not slowing down, it was speeding up. Something was driving the galaxies apart at an accelerating rate, something that acted opposite to gravity on the larger scales. something that had no name yet and no physical explanation that fit neatly into existing theory. Dark energy. The name given to whatever is causing this, which is to say a name for the observation rather than an explanation of the mechanism. And this is the part I find genuinely difficult to fully absorb even now. The discovery of the dominant component of the universe's energy budget, the thing that determines the ultimate fate of every galaxy and every structure within it, came from measuring how bright a specific class of exploding white dwarf appeared at different distances. The most destructive event a white dwarf can produce became the instrument by which we learned that the universe is not doing what we thought it was doing. The 2011 Nobel Prize in Physics went to Perlmutter, Schmidt, and Rees for this. The citation was for the discovery of the accelerating expansion of the universe. The candle is not perfectly standard, as it turns out. The progenitor question, whether all Type 1 supernovae arise from the same mechanism, or whether the double detonation pathway and the merger pathway produce systematically different peak brightnesses, remains genuinely open. If the progenitors vary more than current corrections account for, some of the precision in the darker energy measurement softens. The distances shift slightly. The story becomes more complicated. And the story becoming more complicated does not undo what the supernova showed. It means the instrument is still being calibrated, and the universe is still, as far as anyone can determine, accelerating. The spectrum of a white dwarf should be simple. Gravity so extreme that it sorts every element by weight with a thoroughness no laboratory can match. Heavy elements sinking below the observable surface in hours or years, or at most a few million years depending on the white dwarf's temperature and atmospheric composition. What remains at the top available to spectroscopic observation should be the lightest element present. Hydrogen, if any exists in the outer layers. Helium beneath that. The heavier elements, calcium, magnesium, iron, silicon, the metals that make up the bulk of rocky planetary material, should be invisible, already settled deep below any depth the light can reach. Between 25 and 50% of observed white dwarfers show these elements in their spectra anyway. Calcium absorption lines where calcium should have sunk away billions of years ago. Magnesium, iron, silicon, the signature elements of silicate rock, present in atmospheres where the physics of gravitational settling predicts they cannot have survived for long. The settling timescales are specific and well calculated. In a hot white dwarf, a heavy element introduced to the atmosphere will sink below detection in days. In a cooler one, where the atmosphere is thicker and convection plays a role, the timescale extends to thousands of years, sometimes millions. But millions of years is nothing against the multi-billion-year ages of the white dwarfs, showing this contamination. The metals cannot be original. They cannot be remnants of the star's own composition, held at the surface against the settling that should have removed them long ago. Something is putting them there now, recently in astronomical terms, continuously in many cases. The mechanism that fits the evidence, and fits it cleanly enough that there is not much serious debate about the broad picture, is tidal disruption of planetary material. A rocky body orbiting the white dwarf at some distance is gravitationally perturbed. Something nudges it inward, perhaps the gravitational influence of a surviving outer planet, or the dynamical instabilities that follow when a star becomes a white dwarf and the orbital architecture of its planetary system reorganizes in response to the mass loss. The rocky body drifts inside the white dwarf's Roche radius, the distance within which tidal forces from the white dwarf exceed the internal gravity holding the body together, and there it is pulled apart, not explosively, stretched, shredded, spread into a disk of debris that settles into a flat ring orbiting the white dwarf at close range. The debris disk is warm, heated by the white dwarf's radiation, and it produces a detectable infrared excess around about 1 to 2% of white dwarfs where conditions allow it to be identified. The material in the disk spirals inward over time, accreted onto the white dwarf's surface in a steady flow. and at the surface it contributes its calcium, its magnesium, its iron, its silicon, the elemental composition of whatever rocky body it once was, to the white dwarf's atmosphere, where spectroscopy can read it before gravity has time to pull it down again. What the spectroscopy reads is planetary geology. The ratios of elements in a polluted white dwarf's atmosphere reflect the composition of the accreted body, whether it was iron-rich, suggesting a differentiated body with a metallic core, or silicate-dominated, suggesting crustal or mantle material, or something that resembles the bulk composition of a chondritic meteorite. One white dwarf, GD362, shows evidence for at least 16 distinct accreted elements, examined in detail with JWST spectroscopy in 2025. Each element radio a data point in the reconstruction of something that no longer exists in any other form. Between 1.25% of all white dwarfs are doing this, not as a rare exception, not as a curiosity at the edge of the population, as a common condition. The default, almost, for a white dwarf that has a surviving planetary system and enough time for dynamical perturbations to send bodies inward. And this is the part that shifts something. A white dwarf is often described as a dead star, but a dead star actively consuming the remnants of the worlds that once orbited it, reading those worlds in its own spectrum one accreted element at a time, is not quite what dead usually means. Graveyard is closer, a graveyard where the consumption is ongoing, where what was once a planetary system becomes, slowly and without ceremony, part of the star that outlasted everything else. 3 billion years is a duration that resists intuition. The Earth is approximately 4.5 billion years old, so 3 billion years covers most of complex life's history on this planet, from the first eukaryotic cells through every extinction event, every ice age, every continental rearrangement, to somewhere in the late Precambrian, before animals had yet appeared. It is not a backdrop number, it is a span with texture, and a white dwarf 145 light-years from Earth has been, for the entirety of that span, consuming the remnants of its own planetary system. The system is designated LSPM-J0207 plus 3331, a hydrogen-rich white dwarf cooling for approximately 3 billion years, located in the constellation Aries. In October 2025, a team led by Erica Labourdet published spectroscopic analysis using the Hires instrument on the Keck 1 telescope, finding something that had not been seen before in a hydrogen-rich white dwarf of this age, an active debris disk, still accreting, still feeding material onto the white dwarf's surface, and doing so with a richness of chemical signal that set it apart from anything previously observed in its class. 13 chemical elements detected in the white dwarf's atmosphere: calcium, magnesium, iron, silicon, the expected markers of rocky planetary material, alongside 9 additional elements that together constitute a detailed compositional fingerprint. Not a statistical average, not an inferred bulk composition from 2 or 3 traces. 13 distinct elements, each with its own absorption feature in the spectrum, each contributing a data point to the reconstruction of something that no longer exists as a coherent object. The team identified the accreted material as originating from a differentiated rocky body, one that had, at some point in its history, separated into distinct layers of core, mantle and crust, the way Earth has. The iron content suggests core material. The magnesium and silicon suggest mantle. The body was not a loose rubble pile. It was at least 200 kilometers across, large enough to have undergone geological differentiation under its own gravity. An asteroid in the broad sense, but one whose interior had organized itself into distinct compositional zones before something sent it spiraling inward toward the white dwarf's Roche limit, where tidal forces pulled it apart and spread it into the debris disk now feeding the spectrum. This is where the assumption gets complicated. The standard picture of planetary accretion onto white dwarfs, supported by substantial observational evidence, is that it tends to occur relatively early in the white dwarf's cooling life. Young white dwarfs, still dynamically active planetary systems, rocky bodies perturbed inward by gravitational instabilities in the first hundreds of millions of years. The accretion winds down as the system settles. 3 billion years in, the expectation is a quieter system, the most accessible material already consumed. LSPM J0207 is not quiet. And the question this raises is genuinely open. Is this a late-stage dynamical event, some surviving outer planet finally perturbing a body that had been stable for billions of years, sending it inward only recently? Or does this suggest that planetary systems around white dwarfs remain dynamically active for far longer than current models comfortably predict? The debris disk is the oldest and most metal-rich ever observed around a hydrogen-rich white dwarf. One data point. But a data point that sits in direct tension with the assumption that these systems finish their consuming relatively quickly. 3 billion years of cooling, 3 billion years of whatever the planetary system was doing in the dark, reorganizing, perturbing, settling and unsettling. And then, in the past few million years, which is recent in this context, a body at least 200 kilometers across arrived at the Roche limit and was torn apart, still eating. Not as a metaphor for something persistent in some abstract sense, literally. The spectrum shows it. The elements are there in the atmosphere, sinking as gravity demands, replenished as the disk feeds. 3 billion years, and the star is still swallowing its history. A white dwarf cools because it has no choice. No fusion, no accretion in the isolated case, no internal energy source of any kind. Just stored thermal energy bleeding outward through the surface at a rate determined by the star's mass, its radius, and the physics of how degenerate matter conducts heat. The cooling is not arbitrary. It follows curves that can be calculated, tested against observations, and refined over decades of increasingly precise measurement. A white dwarf of known mass at a known temperature has a known age. Not exactly, but within uncertainties that have been steadily narrowing as the models improve and the data from surveys like Gaia accumulate. The cooling is, in the precise sense, a clock. One that started running the moment the white dwarf formed and has not stopped since. The logic of using it as a clock is straightforward once the cooling models are in hand. Measure the temperature and luminosity of a white dwarf. Apply the cooling sequence for its mass. Read off the cooling age, how long it has been radiating since it first emerged from its planetary nebula. In an isolated system, that cooling age is close to the white dwarf's total age, give or take the relatively brief time the progenitor star spent on the main sequence before dying. For the most massive progenitors that produce white dwarfs, that main sequence lifetime can be subtracted reliably because stellar evolution timescales for those masses are also well understood. Applied to a cluster of stars, a group of stars that all formed at approximately the same time from the same molecular cloud, this becomes something more powerful. In a globular cluster, all the stars share a common age. The white dwarfs present in the cluster have all been cooling since roughly the same moment, modified only by the slight differences in progenitor mass that determined when each one died. The faintest, coolest white dwarfs in the cluster's sequence, the ones that have been cooling longest, set a lower limit on the cluster's age. Find the cutoff where the white dwarf luminosity function drops steeply, where the cooling sequence runs out of objects because beyond that point the white dwarfs would be too cold and too faint to have formed in the cluster's lifetime, and you have a direct age measurement, not inferred from stellar evolution models alone. Read from the objects themselves. This technique has been applied to multiple globular clusters, producing ages consistently in the range of 11 to 13 billion years for the oldest. Applied to the white dwarf population of the Milky Way's disk, the thin disk of stars in the plane of the galaxy, the same method produces an age for when disk star formation became substantial, roughly 8 to 10 billion years ago, depending on the sample and the cooling models used. The disk is not as old as the oldest globular clusters, which is consistent with a picture where the galaxy's halo and earliest clusters formed first, and the organised disk structure came later. And this is the part that carries weight quietly. These age measurements are independent. They do not rely on the cosmic microwave background, or on Hubble constant measurements, or on the ages of radioactive isotopes in meteorites, or on stellar evolution isochrones applied to main sequence turn-offs. They are derived from a completely separate physical process, the cooling of degenerate matter, using objects that preserve their thermal history without contamination from any of the other processes astronomers use to date the universe. When the white dwarf age for the Milky Way's oldest stars agrees with the age derived from the cosmic microwave background, that agreement is not trivial. Two independent methods built on different physics arriving at the same number. Independent confirmation does not prove anything on its own, but it narrows the space of possible errors in ways that no single method can. The clock is not perfect. Uncertainties in the cooling models, in their mass-radius relation at low temperatures, in the composition of the oldest and faintest white dwarfs, these propagate into the age estimates and give them error bars that are real and not merely formal. The bars have been shrinking. The Gaia data in particular has provided enough white dwarfs in nearby clusters to improve the statistics considerably, and the clocks keep running. Every white dwarf in the Milky Way, cooling at its particular rate, carrying the age of the stellar population that produced it in its temperature and luminosity, sitting in the dark, keeping time without being asked to, without being wound, without any mechanism that requires maintenance, just physics running forward, as it always has. Before Gaia, the confirmed white dwarf population numbered fewer than 40,000 objects. This sounds like a large sample, until you consider that the Milky Way is estimated to contain somewhere between 10 billion and 100 billion white dwarfs, the accumulated remnants of every star above a certain mass that has completed its evolution across the galaxy's entire history. 40,000 confirmed objects out of a population that large is not a census. It is a handful of notes from a library whose shelves stretch beyond sight. The catalogue was real and carefully assembled and genuinely useful for the science that could be done with it. But it was radically incomplete, and in ways that were difficult to fully account for because the incompleteness itself was not uniformly distributed. It was biased toward brighter, hotter, nearer objects, the ones easiest to find, which meant the faint and cool and distant majority was almost entirely unrepresented. Gaia changed this not by pointing at white dwarfs specifically, but by mapping the sky with enough precision that white dwarfs revealed themselves through their positions in the colour magnitude diagram. A white dwarf of a known distance, and Gaia's parallax measurements pin down distances to an enormous number of nearby stars with unprecedented accuracy, sits in a specific region of the luminosity temperature plot that no other type of object occupies. Apply the selection criteria to the full Gaia catalogue, and the white dwarfs emerge. The third data release identified approximately 359,000 high-confidence white dwarf candidates, 9 times the previously known population, recovered not through dedicated white dwarf surveys but as a byproduct of mapping everything. Among the things this population revealed was the Q branch, the pile-up of white dwarfs at a specific temperature and luminosity that crystallization theory had predicted, but that required a large enough sample to appear statistically clearly. Fewer than 40,000 objects could not have shown it cleanly. The feature requires enough white dwarfs caught mid-crystallization simultaneously that their clustering stands out above the noise of the cooling sequence. With 359,000 candidates, the Q branch was unmistakable, a direct observational signature of a process occurring inside objects whose interiors are otherwise completely inaccessible. The broader transformation was quieter, but perhaps more consequential for the long term. White dwarf population studies, the mass distribution, the luminosity function, the fraction in binary systems, the rate of magnetic field emergence as a function of cooling age, all of these depend on having a sample large enough to be statistically meaningful across the full range of white dwarf properties. A 9-fold increase in sample size does not just improve the precision of existing measurements, it opens questions that were previously unanswerable because the relevant subpopulations were too small to study. Ultramassive white dwarfs, extremely low-mass white dwarfs, magnetic white dwarfs at different cooling ages. Each category, previously represented by dozens or hundreds of objects, became represented by thousands. And then, in July 2026, does something more specific. A team using Hubble Space Telescope ultraviolet observations confirmed 4 white dwarfs within 20 parsecs of Earth, within 65 light-years, that had not been identified in any previous survey. Not because they were faint beyond detection, because each one orbited a red dwarf companion, bright enough to overwhelm the white dwarf's light in visible wavelengths. The white dwarfs were there, had always been there, radiating an ultraviolet that the red dwarfs did not produce strongly enough to mask at those shorter wavelengths. Once the team knew where to look and at what wavelengths, the white dwarfs were visible. They had simply been hidden behind brighter neighbours. The 4 detections raised the confirmed white dwarf count within 20 parsecs to 153 and pushed the estimated local density to 5.2 white dwarfs per 1,000 cubic parsecs, 16% higher than the previous estimate based on Gaia's second data release. 16% more white dwarfs in the immediate solar neighbourhood than we thought. Not discovered somewhere distant. Here. Close enough that their light has already been travelling toward us for decades. Simply invisible because something brighter was in the way. The danger in white dwarfs, as this video has been tracing, is mostly latent, potential rather than active, conditional on circumstances rather than inherent. But latent danger that you cannot see is a different proposition from latent danger you have mapped and measured. Until recently the map was wrong, it is less wrong now. At the end of the cooling sequence, past the point where any instrument we have built or could build would detect radiation, past the temperature range where any chemical process remains active, past the slow dimming that takes billions of years, and the crystallization that delays it and the magnetic fields that emerge caught from the freezing interior. At the very end, the theory predicts an object that has never been observed and cannot yet exist. A black dwarf. A white dwarf cooled completely. Carbon and oxygen locked in a crystalline lattice. Electrons still flowing through it. Electron degeneracy pressure still holding the whole structure against gravitational collapse. But the thermal energy that once lit the surface gone entirely, radiated away into the surrounding space over a span of time that the universe has not yet lived through. The cooling timescale required to produce a black dwarf is on the order of 10 to the power of 15 years. A quadrillion years. Written out, that number has 15 zeros after the 1. The current age of the universe is approximately 1.38 times 10 to the 10th power years, 13.8 billion. The ratio between the black dwarf cooling timescale and the current age of the universe is roughly 100,000. The universe would need to be 100,000 times older than it currently is before the first black dwarfs could begin to form from the white dwarfs cooling right now. This is not a rounding error or an approximation that might be revised by a factor of 2 or 3. It is a gap of 5 orders of magnitude between where cosmic time currently sits and where it would need to be for this object to exist. Sit with that ratio for a moment. Every event in the history of the universe, the Big Bang, the formation of the first stars, the emergence of galaxies, the coalescence of planetary systems, the entire span of biological evolution on Earth, the present moment fits inside a window that is 1/100,000th of the time required for a single black dwarf to finish cooling. The universe, in terms of the white dwarf cooling clock, is extraordinarily young. Not young in the way popular science sometimes uses the word loosely to mean merely old by human standards. Young in a precise quantitative sense. Barely started if the black dwarf timescale is the unit of measure. No black dwarf exists. Not one, anywhere in the observable universe. Every white dwarf that has ever formed, from the first generation of intermediate mass stars that completed their evolution when the universe was less than 1 billion years old, cooling now for over 13 billion years, the faintest and coldest objects we can still detect, is still somewhere on the cooling curve. Still warm enough, however faintly, to register. Still radiating. Still in the process of becoming something that has not been made yet. This non-existence is not a gap in observation. It is not that black dwarfs exist somewhere we have not looked. too faint to find. They do not exist because the physics that would produce them requires more time than the universe has had. The absence is not empirical, it is temporal. The universe is simply not old enough to have finished any of its white dwarfs, and there is something in that which takes a moment to absorb if you let it. The cooling sequence that white dwarfs are following, the long dimming described earlier in this video, is not a process that has reached any meaningful completion anywhere. The oldest white dwarfs are a few % of the way through their total cooling lives, at most. The story is not near its end. The story, by the measure of the timescales involved, has barely begun. The prediction of black dwarfs is confident in its physics. Electron degeneracy pressure does not require heat to function. A sufficiently cooled white dwarf would remain structurally intact, crystalline, cold, dark, invisible against the background of a universe that will let itself look very different by then. The galaxies will have changed. The stellar populations will have shifted. The longest-lived red dwarf stars will have begun exhausting their own fuel. The prediction is not in doubt. The object is simply waiting for time that has not yet happened. The word gets used because it fits the surface of the thing. A white dwarf has stopped fusing. It produces no new energy. It does not grow, does not change in any obvious way, does not interact with its surroundings unless something comes close enough to fall into it. From a distance, from any distance at which you could observe one without specialized instruments, it is a faint point of light cooling slowly in the dark. It looks finished. It looks like an object that has done its work and is now simply present, diminishing, on its way to being nothing. But finished is not what the previous 24 chapters have described. A white dwarf in the right binary configuration is carrying a thermonuclear trigger on its surface. Not metaphorically. A literal accumulation of hydrogen building under compression, climbing toward an ignition threshold, resetting every few decades or centuries or millennia through a surface explosion that ejects material at thousands of kilometers per second and still survives, still intact, beginning the cycle again immediately, and beneath the nova cycle the slower accumulation of total mass. The walk toward 1.4 solar masses, the walk that some systems are currently on, increment by increment, without any external sign that anything is building. A Type 1. A supernova does not look different from a stable white dwarf in the years before it detonates. Nothing at the surface broadcasts what the interior arithmetic is approaching, and the ones not in binary systems, not accreting, not approaching any limit, are not simply sitting there doing nothing. Between 1.25 of them are actively consuming the debris of their own planetary systems, reading the composition of shredded rocky bodies in their own spectra, accreting the remnants of worlds that formed billions of years ago, and survived the star's death, only to be pulled apart by its gravity in the aftermath. LSPMJ 0207 has been doing this for 3 billion years. The accretion is not finished. The planetary history of that system is still being swallowed, one element at a time, into the atmosphere of the star that outlasted everything else in its orbit. Inside the cooling ones, the ones that appear most passive, something is being generated. As the core crystallizes, the compositional separation of oxygen and carbon drives convection in the conducting liquid surrounding the crystal. A dynamo, running on the energy of freezing, producing magnetic fields that eventually emerge at the surface after millions of years of diffusion. A dead object does not run a dynamo. A dead object does not generate megagauss magnetic fields from the thermodynamics of its own solidification. Here is what I actually think, stated plainly. The word dead implies a quality of inertness, a thing that was once active and is now not. What white dwarfs demonstrate consistently across every physical property examined in this video is that the transition from active stellar life to white dwarf does not produce inertness. It produces a different kind of activity, slower in some respects, operating on longer timescales, not immediately visible at the surface, but active. The thermonuclear trigger is real. The planetary consumption is real. The crystallization dynamo is real. The supernova potential is real, and it is sitting 160 light-years away right now in a system whose merger time is longer than the current age of the universe, but whose existence as a future detonation is already written into its orbital mechanics. And the Sun, the one you have been looking at your whole life, the one responsible for every living thing that has found its way to this video tonight, is going to become one of these, not soon, not in any time frame that touches us, but the core that will remain after the red giant phase, after the planetary nebula disperses, will be a white dwarf, cooling, small, dense, carrying whatever binary configuration it finds itself in or not, processing whatever planetary material remains in range or not, running a crystallization dynamo as it freezes, generating magnetic fields that emerge at its surface millions of years after the freezing begins. Dead is not the word. Quiet maybe, patient, loaded with physics that does not announce itself and does not require an audience. The sky is full of them, cooling in the dark, each one a record, of a star that ended, and a system of processes that did not. Thank you to everyone supporting the Sleepy Physicist on Patreon. Because of you, this place exists.